In everyday English, we use the term energy differently from everyday chemistry or chemistry. So you might say you have a lack of energy, or you might think of electricity as energy, but energy in chemistry is the capacity to do work. And that is actually not just work like going to work, a job, but it's a calculated value. Applying heat is another way to define energy, and this is potential energy versus kinetic energy are the two main buckets to describe energy. So in broad terms, potential energy is due to the position of an object or even its composition. For instance, a piece of wood has a lot of potential energy in it just because it has a lot of bonds that can be broken and produce energy in a combustion reaction. But this ball, this object, has potential energy because you can imagine what will happen when she lets go. This will turn into a different form, which is energy of motion, kinetic energy. So kinetic energy is due to movement. You can see this arrow. But it can also be thought of as a movement at a molecular level, which is heat. So the molecules that we can't see moving faster in an object or in the atmosphere. Now, energy changes from one form to the next here. Potential energy becomes kinetic energy as soon as she lets go. Here's another example with this balloon. This balloon, just by its position, has a bunch of molecules of gas in there, and those gas molecules in there are moving. And what happens when this is let go or opened up? This not moving balloon with a lot of molecules in there that are moving that you can't see, the air molecules will exit and cause that balloon to move, which would be example of kinetic energy when this goes into motion. On the macro scale, energy changes from potential to kinetic energy, and that's due to the law of conservation of energy, which is that the energy of the universe is constant. It is a giant number. I don't even know that number, but it's a giant number, and that's how much energy there is in the entire universe. And this is what we're working with, that this amount of energy just changes forms within that giant number. Heat and temperature, sometimes those are linked to energy too, but they are not. So heat is, we have a couple definitions. Heat and temperature first are not the same, okay? So heat is energy that can be calculated. And heat can flow from something that's hot to something that's cold. And heat is also a calculated value, though we won't do any of those calculations. But heat is calculated based on temperature, which is only one factor, and also the composition of an object, and also the size of an object. Okay, now temperature gets into the molecules of an object, and it's the movement, the average kinetic energy of the atoms or the molecules, or just the particles in an object. And this is something that determines that flow of heat. So you have an object that has, here there's two containers of water. They have the exact same temperature. Okay, and that can be measured based on the molecular motion in this sample of water. However, why is this different heat? Because heat is based on the size of an object as well as the temperature and the composition. So they have the same temperature, they have the same composition because they're both water, but this is more volume, more mass, more water, and so this has more heat as a result. Now, heat is a calculated value, and the units of heat should be always in one of these: calories, and this is going to be linked to nutritional calories, food calories, or joules. And so the conversion factor from calories to joules is that one nutritional calorie or dietary calorie is an uppercase C calorie, which is equal to 1,000 calories that are chemistry calories that we would measure in a lab. And so 1,000 is the metric prefix kilo. So 1 kilocalorie, this is a lowercase c, is equal to 1 uppercase C calorie. That's a nutritional calorie that you see on food labels. The chemistry calories are also even equal to the joules, and so you can use any of these conversion factors. Now, if this J, the joules, is familiar to you, it's because that's a unit of energy that we used in calculations with electromagnetic energy, that we calculated energy as Planck's constant times frequency. That was in units of joules as well. So when you look at the calorie content of any food and it says it's, 500 calories, well, that's actually in chemistry calories, 500,000 calories. So if that doesn't scare you from eating 4 donuts, I don't know what will. Reactions that release heat are called exothermic reactions. So this is an example not of an exothermic reaction, but this idea of water flowing from the top of a waterfall. This is a conversion like the ball we saw earlier. This just moves down potential energy. The water at the top, once it moves down, the waterfall is kinetic energy. And so this is also going to be equivalent to an exothermic process, a chemical reaction that happens naturally. So just like we can't stop this water from flowing down, an exothermic process is a chemical reaction. We can't stop this reaction from naturally producing heat. This is an example of one of the many combustion reactions we'll look at. This is methane, natural gas, CH4, and this has a blue flame when it burns. And so we'll be looking at, just as we saw with flame tests, different colors due to different elements. We'll be looking at burning different things in lab next week. So not all chemical reactions are going to produce heat. Some reactions are the opposite. They're endothermic and heat is taken in. And this might be something that is not detected. It could be on a molecular level and a very low level, but typically an exothermic reaction or an exothermic process feels warm, and this is opposite from the endothermic reaction that feels cold, and it's because this endothermic reaction takes in heat literally from the surroundings, from your hand. If you're holding onto a test tube where there's an endothermic process, it takes the heat from your hand and makes you feel that it's cold. In general, you have a chemical reaction, whether that's endothermic or exothermic, and what happens in the chemical reaction is that bonds are broken and new bonds are formed. Either there's excess energy in the bonds that are formed, and that energy that's excess is released as heat, or there's less, and that will have to absorb energy, and that energy is absorbed as heat with its endothermic. So I mentioned this earlier, the law of conservation of energy is that the energy of the universe is constant, but we'll look at it now in terms of the energy we see that's more specific than potential energy and kinetic energy. So here you can see this example of this spring. So the spring, when it's not in motion, is potential energy. When it's in motion, that's kinetic energy. Here, though, is what we see going on in nature, that when a plant undergoes photosynthesis, it takes in energy and in its bonds, and this is light energy. And that plant then stores that energy that then we can use, either the plant if it's food, or the plant if it is wood, something like that, a tree, and use that in a combustion reaction. So when we're using the energy that's stored, this is a burning reaction, but this will turn into these products of combustion, which we've seen before, carbon dioxide and water. But this is not, the energy of combustion is not coming from nowhere, because the law of conservation of energy, it has to come from somewhere. So where is the energy coming from, the heat and light? It's coming from the bonds of the plant material, and from oxygen, it's coming from this reaction where bonds are broken. The law of conservation of energy reads a lot like the law of conservation of mass. So that law of conservation of mass that chemical reactions obey, mass can't be created or destroyed. Energy cannot be created or destroyed in this law. And this is slightly different. For energy forms are just converted from one form to another. And we will see those forms in this next slide. The major forms of energy we're going to focus on that you see are chemical energy, electrical energy, mechanical energy, radiant energy, and nuclear energy. We'll look at these examples in the work. Chemical energy is from the bonds of chemical compounds. It's due to chemical reaction. When bonds are broken or formed, we have chemical energy was stored in the bonds. And when you see a chemical reaction, that's typically going to represent chemical energy. Electrical energy is due to a flow of electrical charges. So this would be an example of a flow of electrical charges. This battery, which we'll look at batteries in a coming lab, producing the flow of charges. That's the electricity to supply this, which is going to be light energy, and light is a form of radiant energy. Radiant energy is energy that radiates as a wave, and that includes all of the types of energy we've already looked at in the electromagnetic spectrum. Visible light, like this light bulb, but radio waves, X-rays, gamma rays, heat showing a chemical reaction where it's combustion reaction. Remember, fire is burning, so that's chemical energy. And this is turning into heat to boil the water in this flask. And heat is radiant energy, that's infrared. So one thing that we have, mechanical energy, is due to motion and position. It is related to what we talked about earlier, potential energy and kinetic energy. And so when something's moving. And then nuclear energy is one that we don't see commonly. So we see these four forms, but nuclear energy gets its own chapter. It's in alternative energies. And so this is the energy. Nuclear energy is when you break open an atom. So nuclear energy is the energy from within an atom, and that doesn't happen often.